everybody. My name is Zheng Xiangli from Continental University, and welcome to this Snowball Earth workshop sponsored by CCFS, standing for ARC Center of Excellence for Cold Crust Fluid Systems, and by IGCP 648. Yeah. And we have about 70-something registered participants here. And also, this is live casted around the world, so I wouldn't be surprised that there will be more people around the world watching this and this Perth special workshop. Yeah. And Perth is a rather isolated city, you all know, and so it's it's a really great honor for us to have people like Paul come here give us this workshop. And Paul told me that he's going to write a book about Snowball Earth when he's not doing so much fieldwork each year. He's still spending months in the field each year, 7 years after his retirement. So one day he's going to write a book about it. And so hopefully today we will hear an extract of the book, so way before it's coming out. And so before Paul writes up his own book, I'm going to flash out this audio book written about him and Snowball Earth. Anybody has not read it, I highly recommend it. Good reading. Okay, it's about the whole debate. The personal debate about Paul's the pursuit of the hypothesis, and about the early pioneers in this global debate. And of course, Paul doesn't need any introduction, but I'm still going to say a few words about him. Yeah, in science, there are people who make waves, there are people who ride on waves, and there are people all called for anywhere in between the two. And Paul is one of those genuine, true living legends who've been making waves after waves through his career. Yeah, Paul started his career, I think, in late 60s, when I was still a little kid, and started with the Canadian Geological Survey, and worked there for 20-odd years, and worked much with North America, publishing iconic papers like the United Place of North America. You haven't read that paper, you should go look for it. Yeah, then in the early 90s, so when first time I came to Western Australia, and I met him in the first few years. I came here, and Paul and a few others like Ian Dale and Eric Moore started the new hypothesis of Precambrian supercontinents, which we knew nothing before then, or very little. Yes. So the supercontinent in Rodinia, Nuna, the people who think will be working for the last 2 or 3 decades was started by Paul and a few others, and we are still working on it. That's what brought people like me into the Precambrian world. Yeah. Then after spending 20-some years in the Canadian Geological Survey, Paul did a major career jump. He moved to Harvard. And from there, he started the Snowball Earth campaign, and which he's still doing. Yeah, he still spent years in Namibia, and after 7 years of retirement, after a number of operations, he still spent months, more time than most of us in the field, and trotting around the world, and of course he still runs his marathon. Yeah. Okay, without further ado, and I give you Professor Paul Hoffman and his Snowball Earth hypothesis. Yeah.
Thank you, Jung Lee. The reviewer of Gabriel Walker's book in Nature described it as science read in tooth and claw. So I'm really pleased to have this opportunity to discuss in some depth one of the great discoveries of geology, stemming from the theory that the global ocean, the world ocean, was completely ice-covered for tens of millions of years during the Cryogenian period of the Neoproterozoic. That's from 717 until 635 MA. Okay. And just to note a couple of highlights, this is going to be a 4-course meal. And in the first and third parts, I'll be describing new observations which confirm some of the central predictions of the Snowball Earth hypothesis, namely that the glaciations in the Cryogenian were very long-lived, tens of millions of years, and that the glaciations and deglaciations, in other words, the beginning and the end of the glacial periods, were synchronous on many different continents. And a second major prediction was that the deglaciation would occur under extremely high atmospheric carbon dioxide concentrations, because you need a very, very powerful greenhouse effect to overcome the albedo, that is the white color of an ice-covered Earth, which is reflecting most of the sunlight rather than absorbing it. Okay, so these are central predictions of the hypothesis, and I'll be presenting data, none of which existed when the hypothesis was first posed. In the second meal, I wanted to tell you about new results concerning the dynamics of Snowball Earth. This comes mostly from geophysical modeling. Now, this modeling is extremely important because almost every aspect of Snowball Earth, how it functions, is counterintuitive. Okay? And unless we know what the theory actually predicts, no geologist would actually know whether any given observation was either for or against the hypothesis. So it's absolutely essential that we have this normal type of science, the forward type of science, rather than the science that geologists do, which is looking at the results of an experiment long after the experiment has been conducted. A rather strange way of doing science, but a very powerful one, as it turns out. And then in the fourth course, I want to talk about biological aspects, and I'll be making the point that the primary producers in the modern ocean, both eukaryotic algae, principally green algae, and planktonic cyanobacteria, originated during the Snowball Earth period. Okay? And not only that, but that the Snowball Earth events may have been responsible for the rise of oxygen at the end of the Proterozoic, which allowed the ascendancy of multicellular animals like ourselves. Now, a four-course meal deserves a little dessert. And so if I'm still standing, I'll have a little short little dessert at the end where I'll tell you about some new ideas about the dynamics of the assembly of the supercontinent Nuna. I think there are some people in the audience who are quite interested in that. Okay. So this decoration on the side here is simply the frequency of papers per year on Precambrian glaciation over time. And as you can see, this subject goes well back into the 19th century, so it has a long history. There have been sort of some step functions along the way of increased interest. This one here stems from the work of Walter Houchen at Adelaide and Edgeworth David at Sydney around the turn of the last century, which really stimulated interest in Neoproterozoic glaciation. This step function here is due to the English geologist Brian Harland, who first postulated that the ice extended to very low latitudes at this time. And of course, this big surge here is a result of the Snowball Earth hypothesis itself. I should say that much of this surge in publishing activity of the last 15 years has been in vigorous opposition to the hypothesis. But remarkably, in the last year or so, the tide has changed. And I would say at the present time, the vast majority of workers who are active in the field now accept the hypothesis. And that's something that's actually occurred only in the last year or year and a half. So the timing for this workshop is excellent. Now, I want to say I'm going to be covering a lot of ground, and there are questions that are bound to arise. And so I invite you, in fact, I encourage you to put your hand up or just shout out a question as we go along. Okay, I think that will make everything more lively, and it'll be a little bit of relief from my gravelly voice all day. Okay, so I encourage you to ask questions. You go. I may either answer them in the moment or say, just hold it. We will come to it in 40 seconds. Okay, to set the time scale, this is the history of large ice sheets on Earth over the last 3 billion years to the present, with the last 800 million years expanded here. And for this purpose, I've divided the climate history of the Earth into 3 types of situations. And these actually turn out to be well substantiated by a climate dynamical approach. The dark blue represents periods when there were no large ice sheets, such as the early Eocene or the late Cretaceous. The pale blue represent times like the present when we have 2 or more, or even 1 large ice sheet. Today we have ice sheets in Antarctica and Greenland. 20,000 years ago, we also had ice sheets in North America and Europe. And this, of course, are the times when there were large ice sheets on all continents. So this is the Cryogenian period here, and you can see it's in reference to the Phanerozoic timescale, its relationship to the late Paleozoic glaciations of Gondwana, and of course the glaciations of the latter part of the Cenozoic. I'm not going to comment further, but I would point out what to me is the largest anomaly in Earth's climate history, for which there is no really credible explanation, and that is this 1.5 billion year gap when there is no record of ice sheets anywhere. And this is not because of inadequacy of the geological record, because there's lots of evidence of ice sheets before this time. This is a real anomaly that awaits explanation. Now, this is just a diagram to show, to summarize the history of discovery of cryogenian glaciations. This is the date of the discovery for different paleocontinents. That's continents that existed at the time of the glaciations. And you can see that Australia ranks very high on this list. Laurentia South refers to the southern margin of Laurentia at that time. That would be the eastern margin today. You can see that, and this, of course, is Scotland, not North America. North America is quite a bit of a laggard here with respect to other countries. Remarkably, the discovery has been almost linear up until 2003, and I don't expect any more because by now, pretty well all of the continents that existed at that time are now known to have had ice sheets. In the fateful year of 1914, there was an important field excursion in South Australia led by Walter Houchen at the University of Adelaide. Attending this excursion were many of giants of geology of that time, such as Johannes Walter of Walter's Law, Albrecht Penck, the outstanding German glacial geologist, and a young South African geologist named Alex du Toit. This is a distribution of well-established glacial deposits on a regional scale for the two major glacial events of the Cryogenian, which are now known as Sturtian and Marinoan, after Sturt Gorge and Merino Rocks just outside Adelaide. The red dots indicate those areas where the glacial deposits are associated with iron formation, that is, iron oxide formation, which in the latter part of Earth history is unique to the Cryogenian. And note that they are much more widely distributed during the Sturtian than during the Marinoan. I would point out that those areas which are impoverished in these deposits, such as eastern North America, are simply areas where there are no Cryogenian sedimentary rocks preserved, and therefore no record of glaciation. It should not be assumed that those areas were free of ice. Now, here are four people who I think were particularly important in the development of the Snowball Earth hypothesis, and I'll be referring to them from time to time, so I'd like to introduce them now. Brian Harland was an English geologist at Cambridge University. He spent 50 years in the Svalbard archipelago, the European Arctic. In retrospect, I think of one of his important contributions was the observation that cryogenian glacial deposits are intimately associated with thick, shallow water carbonate sequences. And regardless of whether the global climate is warm or cold, carbonate rocks always are preferentially deposited, formed and deposited in the warmest part of the surface ocean. Moreover, these are areas where no mountains existed. And so if you have glacial deposits in the warmest part of the surface ocean at sea level, in a place where there were no mountains from which glaciers could descend, this is a very different climate state than anything we have experienced during the Phanerozoic. Misha Budiko was the young and brilliant head of the Leningrad Geophysical Observatory. He was trained as a physicist. He described himself as an applied geohydrologist. he was interested in the energy balance and the water balance of the Earth, and he conducted the first simple climate model experiments, which showed that there was an instability. In fact, in physics classes for decades, they talked about the ice albedo instability, the fact that if polar ice sheets get too large, so much sunlight is reflected that surface temperatures fall below freezing everywhere, and you go abruptly into a fully glaciated state. The instability refers to the fact that there's no stable ice line in these simple models equatorward of about 45 or 40 degrees. This instability has now been confirmed in at least 7 different coupled ocean-atmosphere general circulation models. But Eco never believed that this had ever actually occurred because for physicists there was no escape. If we had gone into a snowball Earth, you wouldn't have to attend this lecture because we'd still be in a snowball Earth. It was Jim Walker and co-authors at University of Michigan at the Space Research Lab. Jim Walker was a planetary atmosphere scientist who recognized, and in fact they were trying to do something else, but they recognized the importance of silicate weathering feedback as a sort of thermostat that controls Earth's surface temperature and keeps us within the habitable zone despite the fact that solar luminosity has increased 30% over solar system history, over Earth history. And at the end of a very important paper that he wrote in 1981, he pointed out that this thermostatic mechanism, this negative feedback, probably prevented the ice albedo catastrophe, which occurred very easily in models. That probably prevented it from happening, but if it did happen, then there'd be no way to get rid of CO2, and it would simply accumulate in the atmosphere, and eventually there'd be a sufficiently strong greenhouse effect that it would cause the glaciation to terminate. In other words, that the snowball state was self-terminating, and therefore wouldn't be permanent and could be geologically permissible. Okay, so that was a very important thing. And then Joe Kirschfink, the American biomagnetist and paleomagnetist who coined the term snowball Earth and was the first one to say, actually, I think this really did happen in the geological past. He was referring to the Marin. Okay, so Brian Harland. So what Brian Harland observed was in a number of areas, such as northern Namibia, western Mongolia, these 2 glacial events, the Sturtian and the Marin, occur within thick sequences of shallow water and somewhat deeper water, shelfal carbonate rock, shown in this depiction in blue. Okay, and so the important thing is that that means the ice is flowing into the ocean, because these are glacial marine deposits, in the warmest part of the ocean, in areas that are just flat lying at sea level, no mountains. So this shows the latitudinal, which is properly called meridional distribution, or variation with latitude, of non-skeletal carbonates in the Phanerozoic. Okay. In the Cryogenian, of course, there only were non-skeletal carbonates because there were no carbonate-secreting organisms at that time. And as you can see, they occur almost exclusively within 30 to 35 degrees of the equator. In other words, the tropical surface waters, the warmest part of the ocean. So the situation in the Cryogenian would be analogous to having an ice sheet over Australia flowing into the ocean off the northwest shelf of Australia. Okay. Now, that didn't happen in the Pleistocene, not even close. So I'd like to show you a few images of what these glacial and glacial marine deposits look like from the area I'm most familiar with, which is in northern Namibia, the southern part of the Congo Craton, where we have a thick carbonate shelf. Once again, the carbonates are the blue colors, with an abrupt south-facing foreslope, then facing towards the equator. The 2 glacial deposits, the Sturtian, are these red horizons here, and then this is the Marin there. If you're a stratigrapher, you can see that the early part here is related to crustal stretching. The later part is thermal subsidence, broad regional subsidence. And the older glaciation occurred during the period of stretching, this period here, and the younger one during the passive margin. So a much more simple paleogeography at this time. And also the source of the glacial debris, the debris carried by the ice sheets, is just the immediately underlying carbonate, whereas here we have much rougher topography, and glacial deposits are of mixed origin, containing debris of all previous ages, including the Paleoproterozoic basement. Here's the Sturtian in Namibia, polymictic, carbonate exclusively in the Marinoan of Namibia. Okay. So these are glacial marine deposits. So instead of terrestrial moraines, we have marine moraines, also known as grounding line wedges. So the ice grounding line is a place where grounded ice becomes floating ice. And it's in the ablation zone, which is the zone where the ice is melting at the base, where the ice is the warmest. And also most of the debris is carried at the base of the ice if there's not a lot of nunatak sticking up. And so this debris accumulates as the ice melts, either as a melt-out till or seaward of the grounding line as glacial marine deposits. These glacial marine deposits consist of three different types of material that falls out, melts out of the ice shelf or from free-floating icebergs if they existed. Very fine-grained sediment that settles slowly out of meltwater plumes because the ice is melting for much of the extent. So at the grounding line, you have tunnels and meltwater issues into seawater here, and the fine-grained sediment settles from suspension. And then there are lots of debris flows and turbidity flows and things like that because the grounding line is always shifting back and forth on many different time scales. There's lots of sedimentation, so the slope is commonly oversteepened, giving rise to gravity flows. Well, this is an example of one of these deposits look like. There are three components here. The first is this tan-colored stuff. This is very, very fine-grained silt. It's all carbonate, incidentally, because this is on a carbonate area in Namibia. Normal and reverse graded bedding. So this is the plume fallout, just fine suspended stuff that's coming out of these hypopycnal meltwater plumes. The gray beds are turbidity currents. They're graded beds of carbonate, limestone. And then these stones here are the drop stones. Okay, and you'll notice the drop stones are in the plume fallout, but not in the turbidites, because the plume fallout accumulated slowly, and the turbidites were deposited very rapidly, and the ice-rafted drop stones are just falling steadily, and so they tend to accumulate in the slowly deposited material. Here's a nice drop stone. This is a Neolithic limestone. You can see it's dropped down and punctured the underlying strata. The strata that was right at the surface, which is this one, as a result of force of the impact, has been flipped back on itself, in fact, flipped twice. So it's a sort of a double flat. And then these beds have been draped over the top. Now, it's not just the individual lithofacies themselves, it's the way the lithofacies are organized. They're strikingly similar to modern glacial deposits, but the modern ones are at high latitudes and these are at low latitudes. So here we have these stratified material, which is out the front here. This is actually where the grounding line was, where we have lots of massive and sheared diamicton. We have a terminal drape full of ice-rafted debris. Up on the platform, which was exposed above sea level as a result of the large sea level fall when you have all the continents glaciated, you have bits of lodgement till with strong fabrics due to the shearing effect of the flowing ice. Then you have these overdeeps, Paleo Valleys or fjords, with beautifully stratified material with the odd drop stones. Okay, and this is one of these Paleo Valleys here. You can see it cutting the underlying stratigraphy, very thick valley fill in the center, and onlap relationships on the margins of the valley. Okay. This is the kind of work we're doing in Namibia now, lots of measured sections. Okay, this is a simple structural panel. It's a homocline. It's about 60 kilometers long here. We do a measured section every kilometer or so, and it's amazing what you see when you have high-resolution stratigraphy, which the Cryogenian demands. So as you can see, there are a lot of very funny-looking stratigraphic relations here. The mauve color is the Marinoan diamictite. This is a giant moraine, composite moraine. The brown is the Sturtian. This is a Sturtian-age glacial Paleo Valley. This is a carbonate shelf. That's the edge of the shelf. The edge is entirely glacial cut. There's no reef there at all. It probably was, but it's been completely cut off by the glaciation. So the secret of that is this is the Sturtian glacial surface. This is the Marinoan glacial surface. Note the scale. There's over 1,500 meters of local paleotopographic relief here. Okay, without high-resolution stratigraphy, there's no way you'd be able to figure out this stratigraphy. Okay, you can't have enough measured sections. One of the big differences is that unlike the Pleistocene, where grounding lines, say in Antarctica, tended to move back and forth between the outer shelf and the inner shelf, in the Cryogenian, because of the large sea level fall, the grounding lines are way down on the foreslope. And the shelves tend to not have much debris, much glacial debris on them. They're pretty clean. Everything's pushed down into a much more seaward position. Okay, now I want to turn to, now you have a bit of a flavor of what the rocks look like. I would say that it is characteristic of the Cryogenian that the base of the Sturtian or Marinoan sequence and the termination are very sharp and easily recognizable in the field. That's a characteristic feature. So I want to now turn to the results that support major predictions of the hypothesis. So one of the predictions, I'll talk about this in the next hour, why this is true, but the prediction was that the glaciations would have to be long-lived. Basically, it has to be long-lived because it takes a long time to build up enough CO2 in the atmosphere to deglaciate. You need something somewhere between 10,000 and 100,000 ppm. Okay, 0.01 to 0.1 bar. And of course the other, because of the instability, is that the glaciation, at least in the lower latitudes, the onset and the termination should be globally synchronous. So it should have the same age on different cratons. So these are both susceptible to geochronological test. I would also say that before 2004, it was embarrassing that there was not a single Cryogenian glacial deposit that had been directly dated anywhere. Okay, so the geochronological test looked to me like it was never going to happen, actually, but now it has. So that's a remarkable achievement. And it stems from a combination of uranium-lead zircon and rhenium-osmium isochron dating of organic matter in organic-rich sediments. And so these are some of the principal players here, all young. Francis McDonald, he's really spearheaded this revolution from the geological standpoint. Alan Rooney is responsible, and he is now moving to Yale, is responsible for the rhenium-osmium work. Dan Condon, Mark Schmitz, and Shihong Zhang have been particularly important in the uranium-lead work. Okay, now there's a lot on this diagram. This is a summary of the current dates bearing directly on the onset and termination of the Sturtian glaciation and the onset and termination of the Marinoan glaciation. This is the time scale here from 740 to 640. And these little boxes here I've expanded, so that's a 10 million year box. So is this, and that one. This is a 20 million year box. The black symbols are uranium-lead. The red ones are rhenium-osmium. The fat error bars are the very precise ID Timms dates. The narrow ones are the less precise dates. And the gray arrows indicate either maximum constraints or minimum constraints on the onset or termination, respectively. And I've given the paleocontinent on which each of these dates occurs. So as you can see, the onset and termination of the Sturtian are both known to around 1 million years accuracy, based on statistically satisfying all of these data. At around 717 MA for the Sturtian onset, and the termination around 659, indicating that the Sturtian glaciation lasted an astounding 58 million years. That's far longer, I think, than any of us dared to imagine. Some people have suggested that the Sturtian is not a single glaciation, but there are multiple phases of glaciation where you had onsets and terminations. But one of the characteristic features of deglaciation in the Cryogenian is the presence of what are called cap carbonates. Very distinctive carbonate layers that sit directly and sharply and globally directly upon the glacial deposits. Nowhere have multiple cap carbonates been described from either the Sturtian or the Marin Owen. There's only one Sturtian cap carbonate, and everywhere it's been dated, it's 659. That's all these red ones here. The Marin Owen onset is the one that hasn't been nailed yet. It has to be somewhere between 650 and 640. The termination is nailed at just over 635. We're greedy now. We really want to get this one. But what we can say at present is the Sturtian lasted 58 million years, and the Marin Owen lasted somewhere between 4 and 15 million years. If you prefer to see the numbers, these are the numbers for the cap carbonates of the Marin Owen and Sturtian age. That's the termination. And as you can see, these are statistically indistinguishable. And references in the paleocontinent from which they come and the method. Any questions on the sheet? Yeah?
Well, I have a question. If you can go back to the last slide.
Yeah.
The onset of the Sturtian, there are two analyses, or two aspects, I guess, from Laurentia. One that dates the beginning of the onset.
Yeah.
And the other that dates the
Correct.
end of the offset.
Yeah.
Or constraining the offset.
Yeah.
Are those from the same stratigraphic section, or are those from different sections?
Same section.
The same section.
Same section. They're from the Mount Harper inlier in central Yukon. So this is from a rhyolite that is below the first glacial deposits in the succession. And this one, 716.5, this is 717.5, this is 716.5, comes from a rhyolitic tuff that is a few tens of meters up within the glacial deposits. And moreover, in the same area, although not in exactly the same section, you have a constraint from the cap carbonate. So in fact, it is in northwestern Canada is the one place where you have both the onset and the termination nailed in the same area. So no issue about correlation. Yeah, good question. Okay, so to give you a feel for that, if the Marin Owen ended today, then the Sturtian began well back in the late Cretaceous, and the Sturtian would have lasted from early Campanian until the end of the Oligocene, to give you a sense of the time scale. And the Marin Owen cryocron, I call these cryocrons, these periods when the world ocean was totally ice covered. The Marin Owen cryocron began in the middle Miocene, and so its time scale would be very comparable to that of the extant East Antarctic ice sheet, which has been in permanent existence for 14.8 million years. So broadly similar. So now that we have a time scale, we can do all sorts of things that we couldn't do before. So this is from a paper that's in press in Geology. I expect it'll be out in the next issue, showing the sedimentation rates. So this is a plot of the net thickness of a glacial interval as a function of the duration or the integration time of that interval. In other words, how long the glacial period was over which you're integrating the thickness to get an accumulation rate. And it's important to do that because if you want to compare sedimentation rate for the entire Marin Owen or the entire Sturtian, and we have to use the entire interval because we have no way of knowing yet how much time within either of these cryocrons any given sequence represents. So we can only take the total thickness and then divide it by the duration of the entire cryocron. You have to compare it with Phanerozoic analogs. So these dots, the red dots, are glacial records from over 10,000 Phanerozoic occurrences. The gray band are all terrigenous shelf sediments. You have to compare with comparable durations because not surprisingly, the accumulation rate, which are these lines here, constant accumulation, the accumulation rate declines as the integration time increases. So what's striking here is that the Marinoan and Sturtian rates of accumulation are between 3 and 10 times slower than any Phanerozoic glacial deposits integrated over the same time period. Okay. And that's pretty impressive considering that these Phanerozoic ones, which are the late Paleozoic glaciations of Gondwana and the late Cenozoic glaciations of the northern hemisphere, those are mostly polar and subpolar ice sheets, whereas the Cryogenian ones are mostly low-latitude ice sheets. So the low-latitude ice sheets were actually moving and depositing sediment at a much lower rate than polar ice sheets did in the Phanerozoic. Okay, and so that's suggesting that although these deposits are quite impressive, you know, they're up to hundreds, even a few thousands of meters thick, when you integrate them over the time of the glaciation, the accumulation rates are extraordinarily slow. And that's an indication of the fact that under the cold snowball conditions, the atmosphere is extremely dry. And so although there is a hydrologic cycle, ablation and condensation of snow and snow accumulation, it's at a very, very slow rate. And therefore, the rates of sediment deposition are also very slow. Okay, so what to make of these geological observations? And of course, remember, please, that this time scale, we've only had this, you know, for 18 months now. I mean, not all those dates, but these dates have really been coming together very, very recently. Oh, sorry. Okay, so I wanted to talk a little bit about some ideas prior to Snowball Earth, to try to explain low-latitude glaciation. So I think the first and most interesting explanation was the one that was developed over many years by George Williams at the University of Adelaide, and sometime exploration geologist. And he tried to relate low-latitude glaciation to a large obliquity of the Earth's orbit. Okay. So with the present obliquity, we have the annual insolation, that is, the solar heating is strongest at the equator and weakest at the poles. But if the obliquity is very large, greater than 54 degrees, the equator actually becomes cooler than the poles in the mean annual. The reason for this is because in large obliquity, during the summer, the sun is directly overhead all the time, and it gets really hot. In fact, on land, it gets above the boiling point. And so the mean annual is actually warmest at the poles and coldest at the equator. And so George Williams promoted the idea that preferential low-latitude glaciation was a product of high obliquity. He originally suggested that the glacial periods represent periods of high obliquity, and the Earth went back and forth between high and low obliquity. It turned out this is not possible for orbital dynamic reasons. If you ever get into low obliquity, you can't get out. It's because of the gravitational interaction of the equatorial bulge of the Earth and the Moon. Okay, Mars can have chaotic obliquity, but Earth can't because we have the large Moon. But it would be possible to have chaotic large obliquity throughout Precambrian time until the Neoproterozoic, and then quickly get into low obliquity, because we know that from fossil record that during the Phanerozoic we've always had a normal temperature gradient. And nobody's figured out how to do that, but I don't think we should rule that out on theoretical grounds. Okay, so this is a very interesting idea. I think it does, however, have a couple of insurmountable problems. One is from the climate implications of the theory itself, and the other is from an observational test. The problem from the climate standpoint is that with large obliquity, you have very hot summers everywhere. And even in the coldest part in the equator, at equinox, it's just like at the equator today. The sun is going directly overhead every day. And then at solstice, it's cooler because the sun is just sitting on the horizon the whole time. But the hot season is hot everywhere. That makes it very difficult to accumulate ice. Remember, the Milankovitch climate idea was that to get an ice sheet to grow, some of the winter snow has to survive the summer melting season. Okay, so the ice can grow incrementally. In the high obliquity state, that's almost impossible. In fact, in models, and there's a very good model was recently published of climate in high obliquity, you have to turn down the radiative forcing of the CO2 so low that you go directly into snowball Earth. So at high obliquity, from a climate modeling perspective, this is a modern coupled ocean atmosphere, GCM, you're either in snowball or you have no ice at all. There's no partial ice cover possible in the model with high obliquity. The other is the observational test. Okay, because in high obliquity the temperature gradient is reversed, coldest at the equator, hottest at the poles, the Hadley cells are reversed. Okay, that means you have atmospheric downwelling at the equator and air is rising in the subtropics. So the Hadley cells are doing exactly the opposite of what now they go like this. At that time they go like that. And that makes the prediction that evaporite should be on the equator. Okay. And Dave Evans looked at the paleomagnetically defined paleolatitudes of evaporite deposits over time from 2.5 billion years to the present. The size of the circle is an estimate of the original volume of the deposit. This is the Cryogenian here. And as you can see, they've always been in the subtropics. There are no evaporite deposits on the equator. Okay, so I think this is an observational test that shows that high obliquity has not occurred in the last 2.5 billion years. Now, another idea that also came from modeling, and in this case, a sort of simplified coupled GCM that was coupled to a carbon cycle model, is that the snowball Earth was the result of an increase in the burial of carbonate and or perhaps organic matter, which caused a lowering of atmospheric CO2 and a cooling of the climate, that at least made the Earth more susceptible to this runaway glaciation. So this is a model that was published in Nature some years ago, and it related this cooling effect to two things. First of all, the breakup of the Rodinia supercontinent, and that had the effect of making a lot of areas that were previously dry a lot wetter, and so you got increased weathering. And also you had an increase in continental margins and sedimentation globally, and if organic matter burial scales with anything, it scales with sedimentation rate. And so the idea is with more sediment being deposited, more organic matter would have been buried, and both the intensified weathering and the organic burial would lead to a drawdown of atmospheric CO2 in a colder climate. And moreover, it was also suggested that large flood basalts, large areas of basalt lava that were associated with the breakup of the supercontinent would be particularly susceptible to intense weathering, because basalt is much more weatherable than granite, provides the right cations, and also has a lot of phosphorus, which stimulates productivity and increases the potential for organic burial. So this was something that came out of a model, and I think now has been substantiated, first and foremost by Lee's paleogeographic reconstructions done here, showing that this period from the onset of the Sturdian to the end of the Marin does indeed coincide with the breakup of the supercontinent Rodinia, which was situated at very low latitude. And having this paleogeography, we can now plot all those glacial deposits that I showed you earlier on this paleogeography, and these are the red stars for the Sturdian and the Marin. And as you can see, the glacial deposits occur at pretty much, well, all latitudes, including latitudes right on the equator. And we've tested this paleogeography against sedimentary facies, and it seems to stand up remarkably well, I must say. I guess the only areas that are lacking, and once again, mostly because of lack of record, are these very high latitudes here. That wouldn't be so surprising because these latitudes, as we'll see, are farthest from sources of moisture. These would be areas where the ice sheets would be least active. Okay. So this paleogeography is pinned, at least in latitude, by direct paleomagnetic data on the glacial deposits. This is a particularly important one here. It's the one we have for the Sturdian that nails Laurentia right on the equator, and there's Sturdian glacial deposits pretty well all around the periphery of Laurentia. And this is the paleopole now for the Franklin Large Igneous Province at 715 and you'll remember that number, the emplacement of the Franklin large igneous province coincides exactly with the onset of the Sturtian glaciation. In fact, the area we discussed, the Mount Harper area, where those dates come from, is right in there, and that's part of the Franklin large igneous province, at least chronometrically. Notice that Ted Irving's old paleopole from 1971 is statistically indistinguishable from the modern one, 78 sites. It's a well-established pole. So here's the extent of this large igneous province. It extends from Alaska to northwest Greenland. There's just one erosional remnant of lava preserved, but lava probably originally covered much of this area, and that's the paleo equator. And these are the Sturtian glacial deposits in the Mackenzie Mountains. And the Yukon, the Mount Harper area is right there. Okay. So the importance of the Franklin large igneous province is that it was emplaced right across the equator, where weathering is most intense. And so this would be a very good way of triggering CO2 drawdown, is from weathering of that basalt. Now, there is another idea that's being worked on in present. There's a paper by Robin Woodsworth and Francis McDonald, I think has recently been submitted. It's in peer review at the moment, which suggests a more direct volcanic link with glaciation. And that is the idea that large flood basalts produce thermal plumes above fissure eruptions that are surprisingly effective at injecting sulfate aerosol into the stratosphere. And that has a strong cooling effect. In the troposphere, the sulfate doesn't last very long. It rains out. But in the stratosphere, the residence time is long, and it scatters sunlight, and it's a significant cooling effect. You'll remember Mount Pinatubo. Now, the importance of the Franklin large igneous province is not so much the lava itself, but the fact that those lavas were emplaced through a thick sedimentary succession which has several sulfate evaporite layers in it. It's a shaler group. And the Siberian Traps large igneous province produced global warming because it went through a sequence full of coal. And this one probably formed a cooling effect because it went through a sequence full of evaporites. Same with the Triassic-Jurassic boundary, the Central Atlantic igneous province, also associated with cooling. Someone should look for those evaporites there. So observations have given legs to this idea that breakup of the Rodinia supercontinent was very important in at least making the Earth more susceptible, if not the proximal trigger itself, for the Sturtian glaciation. Okay, this has also been supported by isotopic data. These are from Alan Rooney's work in northwestern Canada. These are sediments directly below the Sturtian glaciation. And the strontium isotope values here are extremely non-radiogenic, down below 706. And similarly, the osmium isotopes are extremely non-radiogenic. And Grant Cox has work, I'm not sure whether it's out yet or not, on neodymium in shales, also showing extremely non-radiogenic values consistent with basalt weathering dominating the weathering flux in the lead into the Sturtian glaciation. Okay. Now, this is a rather busy diagram. This is a climate here, non-glacial, and that's the Sturtian, the Marin. It's a time scale here. Detrital zircons, there's a low in here, suggesting that volcanic outgassing rates might have been low going in. This is the continental area at less than 15 degrees paleolatitude. This is a high that would also tend to intensify silicate weathering. This is the breakup of the Rodinia supercontinent. This is Rodinia here, formed around 1 billion and then started to break up around 740 or so. Rise in strontium isotopes. These are the large igneous provinces. That's the Franklin. They are northern Canada, which is the last of a cluster of them. Carbon isotopes, which take a tumble from predominantly organic burial to release. And then this is a idealized cladogram for metazoans, showing last common ancestor of Metazoa might well be Cryogenian in age. We'll come to this later. Okay. Now, although it's very attractive, I think, to relate the Cryogenian to the breakup of the Rodinia supercontinent, and possibly the low-latitude glaciation associated with the great oxidation event in the Paleoproterozoic with the breakup of the Canora supercontinent, there doesn't seem to be any climate consequence to the breakup of Nuna, the Orosirian supercontinent. And the Paleozoic glaciations of Gondwana land seem to be more associated with the assembly of Pangaea than with its breakup. So there must be factors other than supercontinent breakup at work to explain this, I believe. Another thing that I think still has yet to be properly explained is why most of the iron formations occur in the Sturtian and few, if any, occur in the Marinoan. I would say the age of this is still not 100% certain, although it does look like it's Marinoan. That would be one exception. And there is the large difference in age between the two events. Remember, the Sturtian was 58 million years and the Marinoan was 5 to 15 million years. Now, it's possible that there's not great significance to this. Because you need an enormous amount of CO2 to deglaciate, and the climatic consequences or relationship to CO2 is a logarithmic one. In other words, for each unit of climate change, you'd have to double CO2. And so at a very high concentration, it takes a long time to double CO2. Nevertheless, I think it's, and a lot of people are thinking about why it is that the Marinoan was so much shorter. I expect it has something to do with the weathering of the seafloor that occurred during the acidification associated with the Sturtian glaciation and the weathering of the continents in the greenhouse aftermath of the Sturtian glaciation that meant that rocks both on the seafloor and the continents were pretty deeply weathered in Marinoan time, and therefore there were not very effective sinks for CO2. And so CO2 rose more rapidly in the atmosphere. But that's a conjecture. We'll probably come back to that. So these are some of the differences between the Sturtian and Marinoan. And a lot of people are scratching their heads trying to think about why these differences should occur. And it's a very nice situation for science where we have a whole bunch of anomalies that are broadly related, because you'd like to think if you could get the right explanation for one of them, that explanation would probably explain a lot of the others as well. It's always a good indicator you're on the right track when an idea you have for one problem, solves a bunch of other problems you weren't even thinking of. So the Marinoan has a preglacial carbon isotope excursion. The Sturtian does not. There's a large igneous province before the Sturtian, but not before the Marinoan. Big difference in duration. Prior glacial hiatus, like 1.5 billion years without any glaciation before the Sturtian, whereas the Marinoan had barely recovered and it's back under ice again. Iron formations mostly in the Sturtian. Better developed carbonate in the Marinoan from a number of different perspectives. So there are a lot of differences here that people are working on. So let's summarize the geology. Here's, I think, what we can say at the present time based on geological evidence, including geochronology, paleomag. So tidewater glaciers, that's glaciers that were flowing into the ocean, existed on tropical margins where no mountains existed. So right from that basic geological observation, we know something very strange is going on. Both cryochrons were long-lived, and their terminations and onsets, were globally synchronous, at least synchronous on several different cratons now. Average sedimentation rates over cryochrons, 3 to 10 times slower than Phanerozoic rates, despite their much lower paleolatitudes. Marinoan, much briefer than the Sturtian. This is what I just told you. And what we'll learn in the next hour is that although white ice sheets waxed and waned during the cryochron, there's no evidence in the form of cap carbonate for a global deglaciation within a cryochron. Okay? And I think the most reasonable assertion at present is that these cryochrons, 58 and 4 to 15 million years, represent periods when the ocean was globally ice covered. There were cracks, but not large areas of open water, because it turns out that that's unstable. The ice will flow in. Okay? So let's end the first session, and I'd be happy let's see, yeah. So we have a few minutes for questions. Desperate for coffee. Yeah.
I guess more in terms of the holdouts. You said that it was just recently when now the community has come to a consensus that this is real. What was the evidence that pushed those holdouts over the edge just recently?
Yeah, I think it was definitely the geochronology. I never really considered it that effective a test. First of all, I never expected that geochronology would be anywhere near this good. And you know, I've been working with uranium-lead people, including some of the pioneers, for a long, long time. I mean, uranium-lead geochronology converted what I did from, you know, drafting, good draftsmanship, as Dan McKenzie used to say, Hoffman's a good draftsman, to hypothesis testing. But I think the geochronology was actually the thing, because the geologist kept saying, show me the dates, show me the dates. I thought that was just stalling for time, frankly. Now, it wasn't a conversion. Remember what Max Planck said, science advances one funeral at a time. Okay? So I had a list of the 45 people or so, PIs, that were working on the Neoproterozoic, who actually, in writing, took a stand, either for or against the Snowball Earth hypothesis during the period of hysteria, as I call it. And there's about 85% against and 15% for. The ratio is not important. What's important is not a single person on that list has changed their mind. Not one, including me. So what's happened is it's a completely new group of people now who are the active workers. And among those people, yeah, I think there have been a lot of people have shifted, but they had never taken a stand. You know, the problem is people take a stand right away. All along I've been saying, wait, hold on. We don't know even what the predictions are yet because we don't understand the hypothesis well enough. So it's like small children. Don't judge them too soon because you have no idea what they'll be like when they grow up. Yeah.
One question. What's happening in between the two?
Yeah, that's a great question.
Is there a global pattern to the type of geology or
Yeah, so in Namibia, where this sequence between is beautifully developed and exposed, and we've been studying it for a long, long time, there are lots of cycles, probably Milankovitch-driven cycles, but there's no evidence for large amplitude sea level fluctuations. So it looks like there's no ice at all. Okay? So it appears that in the Cryogenian, you're either in Snowball or you have no ice. You're not in the state we're in today. And I think that may be due to the paleogeography. I should have paused a little more when I had Lee's paleogeographic map up because there are no high latitude continents at that time. Almost all the continents are between 30 degrees north and 45 degrees south. So not unlike Ordovician paleogeography, except there are no south polar continents. And so that means you need a lot of sea ice before you even get any ice sheets. Okay, so you're very close to the ice albedo instability, which I'll talk about next hour, before you have any ice sheets. So you're either in Snowball or you have no ice. Otherwise, they're normal sediments. They're different because we now have this 10 million year window that we can identify all over the world as being isochronous. They're all different kinds of sediments, as you'd expect. But of course, in the lower part, it's dominated by carbonate in the aftermath of the Sturdian. And I'll explain in the third hour why the Snowball hypothesis provides an elegant and beautiful explanation for these cap carbonates. And it has to do with ocean acidification. Yeah.
I noticed on your map that you had I noticed on your map that you had the concentration of iron ore deposits in Central Australia, whereas you know the great predominance of iron ore deposits is in the northwest. But is that just because that's so generalized?
No, that's because these only show iron formations that are directly associated with the Cryogenian glacial deposits. So the ones up here in the Pilbara, in the Hammersley ranges, are much older, and they're not associated with glaciation.
I see.
Yeah.
Thank you, Paul. Just on the intense weathering during the Sturtian, is that more intense physical weathering rather than chemical weathering? It seems counterintuitive. Cold weather, you don't seem to have.
Yeah, so that was during the Sturtian. I'm referring only to seafloor weather.
Yep.
It's true that the seafloor, that the bottom waters are also cold, but they're not that much colder than today, because bottom waters are near the freezing point right now. So Snowball is a little bit colder, mostly because it's a lot saltier, because you've taken so much water out. So Snowball, seawater bottom, well, actually the Snowball Ocean is completely isothermal, surprised everyone, would be around -4 degrees, depending on the salinity. The main reason for thinking that the weathering would be intense is the acidification. So pH may have been 6.5. And so at cold temperatures, the pH is very important. It's not so important at elevated temperatures. In the Cretaceous, I don't think the pH made a big difference because the bottom water was so warm. But when the bottom waters are cold, a pH matters a lot. So if you weathered most of the seafloor, and you could have weathered a lot of it because there was less pelagic sediment at that time because there were no calcareous nanoplankton, you would only have had 10 million years of new oceanic crust produced after the Sturtian glaciation before you went into the Marin Owen. The continental weathering would have occurred in the greenhouse aftermath of the Sturtian glaciation, because you get rid of all the ice very quickly, and I'll show you the reasons why the deglaciation is extremely rapid, much faster than you can get rid of the CO2. So one of the interesting predictions is that this long glacial period, when surface temperatures are way below freezing everywhere, is immediately followed by the hottest climates the Earth has ever experienced, because you have 100,000 ppm of CO2 and dark surface. So tropical sea surface temperatures are in the 50, 55 degree range.
Hello, Paul. Thank you. What about the sea level? Sea level.
Yeah.
Because maybe
it all depends on how much volume of ice sheets you have above sea level. And so if all the continents were covered by an average of 2 kilometers of ice, which is the thickness of the East Antarctic ice sheet above sea level, about just 2.1 kilometers, then you would have about 1 kilometer of sea level fall.
Both the onsetting of the snowball Earth and the deglaciation, the de-snowball Earth, I mean, whatever, the way out, both happened very quickly, synchronous within 1 million years. I just wonder whether is evidence pointing to the whole process covering the entire globe happening within 1 million years, or that's because the record at the moment are predominantly from the low or medium latitude. So we only have a record of the lower latitude zone.
Yeah. I'll talk about this in more detail in the next hour. The only GCM that's really looked at how long it takes to go from the ice albedo instability, that's an ice line around 40 degrees, to fully ice covered, suggests it might be on the order of 150 years. The model that probably doesn't have real physics very well of, ice margin physics is very complex and it can't be captured in a global model very well. But it could be on that order. The deglaciation, I always say less than 10,000 years. That's just because Holocene deglaciation was around 10,000 years. This is bound to be faster because CO2 is way higher and most of the ice sheets are at low latitude where the insulation is strongest. I would guess the deglaciation, and it'll be global, will probably occur in order of 1,000 years, 2,000 years, but it hasn't been, models still can only model equilibrium states. A completely non-equilibrium state like glaciation and deglaciation, that's for models of the future. You can't really do that now.
could you hold the question for? We have more time to ask questions. I think we should.
Let's take one more question.
One more question.
Yeah.
Thanks, Paul. I just wanted to know about the obliquity and eccentricity of the Earth's orbit.
Yeah.
So has that been completely blown out now? Because that was the standard theory about why glaciations happened and deglaciations happened. So has that...
Well, I think the two problems I mentioned, the fact that it's very difficult to get partial glaciation with large obliquity because of hot summers, and the evaporite test, I think those are really insurmountable obstacles. As I mentioned also, no orbital dynamicist has been able to, and some have tried, to change the obliquity from high to low very abruptly. So, yeah, I think it's a... Sorry, the obliquity. Oh, you said eccentricity. Oh. So what was the question about eccentricity?
It was just different kinds of wobbling of the Earth's orbit. The major theory was, and apparently it was supported, but I don't think it is now after what you're saying. But that was the major theory about glaciations. Was like,
you mean the George Williams theory?
Yeah, well, one of the major things was Earth's orbit.
Yeah, but that was the obliquity of the orbit, not the eccentricity.
But the eccentricity was
okay, so the obliquity is the angle between the equatorial plane and the ecliptic plane of the solar system. Right. So in his case, he made that very large.
So the eccentricity was...
the eccentricity is how elliptical, the difference between the closest approach and the farthest approach of the Earth from the Sun.
Major part of the theory of...
Well, the others, like precession and eccentricity, could also have changed now that we are more relaxed about the possibility of movements of the orbits of the gas giant planets.
Okay, so not much has been done in that sector?
Um,
Because we're concentrating on the Earth a lot, but we're not really looking at the outside forces.
Yeah, but remember that eccentricity makes no change whatsoever in the annual insolation. We receive exactly the same amount of sunlight, solar energy, irrespective of the eccentricity in the global average. The eccentricity will affect the seasonality. And that does have an effect on, ice sheet growth would be favored by a low eccentricity.
I think you have a break and you come back at 11 o'clock.